The wafers are immersed in an etching solution. Specific areas of the surface are protected by a mask layer. In the opening of the mask, the etching solution reacts chemically with this single crystal material. The etch rate is highly dependent on the crystallographic direction of the material. Depending on the etching solution and temperature, etching along the 100 and 110 planes of silicon is 10 to 100 times faster than along the 111 plane. One feature of the silicon anisotropic etch is that the process stops by itself when all slow etching 111 planes meet. The cavities formed by wet anisotropic etching are shaped along the 111 planes of the silicon and result in the characteristic V-shaped grooves and holes. The etch process is highly sensitive to any misalignment of the mask with the crystallographic orientation of the wafer. Complex forms can be produced by exploiting anisotropic etching of both sides of the wafer, the etching operations being carried out simultaneously or sequentially. For the latter, backside protection of the wafer is needed and can be done either by applying a coating of mask material or by mounting the wafer on a specially designed holder. Potassium hydroxide solution, or KOH, is commonly used for the anisotropic wet etching of silicon. It is a low-cost and easy-to-handle chemical and produces an average etch rate of 16 microns per hour. The main drawback of KOH is its total incompatibility with standard IC processes, preventing further wafer processing on a standard production line after etching. An alternative to KOH is ethylene diamine pyrotechnol solution, or EDP, which is compatible with IC production lines but is an expensive and highly toxic product. Tetramethyl ammonium hydroxide, or TMAH, is used more and more as etching solution for anisotropic etching of silicon. It is non-toxic, IC compatible, and low cost. In order to selectively etch the desired structures, a patterned layer of masking material is deposited on the wafer surface. It must be resistant to the etching solution. Silicon dioxide and silicon nitride offer good protection properties and are two commonly used materials. Note that silicon dioxide shows poorer resistance to KOH than silicon nitride, and a rather large thickness is required for long etch times. Typically, a 2-micron oxide is needed to etch 380 microns of silicon. On the other hand, silicon dioxide resistance to EDP and TMAH is excellent, and it can be easily removed in a hydrofluoric acid solution. Silicon nitride shows excellent resistance to all commonly used etching solutions, but is quite difficult to remove. It must be etched by hot phosphoric acid or by plasma etching. Wet anisotropic etching of silicon is a slow process. With a typical rate of 0.3 microns per minute, it takes up to 24 hours to produce a several micron thin membrane, starting from the backside of the wafer of typically 380 microns thickness. Aside from simply controlling the etch time, say the duration of the wafer immersion, various etch stop techniques have been developed to precisely control the thickness of the remaining material, which is usually a critical functional element of the final device, such as the membrane of a pressure sensor. Time etch stop is the easiest technique, where the time needed to reach the target thickness is calculated. For reliable results in practice, the wafers are removed from the etch bath and the remaining thickness is measured to determine the effective etch rate. Several iterations are usually done, and the remaining etch time is recalculated each time to reach the target thickness with good reproducibility. The boron etch stop technique uses heavily boron-doped silicon, which exhibits a much lower etch rate than low-doped silicon, to stop the process at the interface. The remaining structure is then made of heavily doped silicon. Its thickness can be very well controlled during boron diffusion. A major drawback of this technique is that no electronic devices, such as resistors, can be integrated in the doped material. Other thin film materials deposited on the backside of the wafer can be used as etch stop layers. This is known as thin film etch stop. Silicon nitride is normally used if the remaining structure will have a mechanical function, because its mechanical properties are superior to those of silicon dioxide. A particular case of thin film etch stop techniques is found in the use of silicon on insulator wafers. The etch process stops at the buried silicon dioxide layer, leaving a well-defined silicon layer as the functional structure. Electrochemical etch stop can be effectively performed on a normally n-doped silicon layer in which resistors can be integrated. Usually, an epitaxial n-doped layer of silicon is grown on a p-type substrate to form a p-n junction. The etching will stop at the junction if a reverse voltage is applied. Electrochemical etch stop is a precise, reproducible, and reliable technique, but requires complex apparatus to electrically contact the wafers in the etching solution.